Hi, this is Meghna from CSCC. My roll number is 21BQ1A05I3. Today we will discuss about alpha beta pruning. Alpha beta pruning is a modified version of the min-max algorithm. It is an optimization technique for the min-max algorithm. As we have seen in the min-max search algorithm that the number of game states it has to examine are exponential in depth of the tree. Since we can't eliminate the exponent, but we can cut it to half. Hence, there is a technique by which without checking each node of the game tree, we can compute the correct min-max decision, and this technique is called pruning. This involves two threshold parameters, alpha and beta, for future expansion, so it is called alpha beta pruning. It is also called as alpha beta algorithm. Alpha beta pruning can be applied at any depth of a tree, and sometimes it not only prune the tree leaves but also entire subtree. The two parameter can be defined as alpha, the best choice we have found so far at any point along the path of maximizer. The initial value of alpha is minus infinity. Beta, the best choice we have found so far at any point along the path of minimizer. The initial value of beta is plus infinity. The alpha beta pruning to a standard min-max algorithm returns the same move as the standard algorithm does, but it removes all the nodes which are not really affecting the final decision, but making algorithm slow. Hence, by pruning these nodes, it makes the algorithm fast. The important and main condition for alpha beta pruning is alpha greater than or equal to beta. Key points about alpha beta pruning. The max player will only update the value of alpha. The min player will only update the value of beta. While backtracking the tree, the node values will be passed to upper nodes instead of values of alpha and beta. We will only pass the alpha beta values to the chain nodes. Working of alpha beta pruning. Let's take an example of two-player search tree to understand the working of alpha beta pruning. In step 1, at the step, the max player will start first move from node A where alpha is equal to minus infinity and beta is equal plus infinity. Initially we assign the value of alpha and is minus infinity and beta is equal to plus infinity. These values of alpha and beta pass it down to node B where again alpha is equal to minus infinity and beta is equal to plus infinity, and node B passes the same value to its child D. Here the picture. Here we take the tree as A and the child nodes is B and C. Initially we assign alpha is equal to minus infinity and beta is equal to infinity. Max, min. In step 2, at node D, the value of alpha will be calculated as it turn for max. The value of alpha is compared with firstly 2 and then 3. And the max of 2, 3 is equal to 3. We will be the value of alpha at node D and node value will also 3. In step 3, now algorithm backtrack to node B where the value of beta will change as this is a turn of min. Now beta is equal to plus infinity. We'll compare with the available subsequent node values. That is min of alpha comma infinity comma 3 is equal to 3. Hence at node B, now alpha is equal to minus infinity and beta is equal to 3. Here's the picture. At child node D, the turn is max. In the next step, algorithm traverses the next successor of node B, which is node E, and the values of alpha is equal to minus infinity and beta is equal to 3 will also be passed. Step 4. At node E, max will take its turn and the value of alpha will change. The current value of alpha will be compared with 5. So max of minus infinity comma 5 is equal to 5. Hence at node E, alpha is equal to 5 and beta is equal to 3, where alpha greater than or equal to beta. So the right successor of E will be pruned and algorithm will not traverse it and the value at node E will be 5. In step 5, Algorithm again backtrack the tree from node B to node A. At node A, the value of alpha will be changed. The maximum available value is 3, as max of minus infinity comma 3 is equal to 3 and beta is equal to plus infinity. These two values now passes to right successor of A, which is node C. At node C, alpha is equal to 3 and beta is equal to plus infinity. And the same values will be passed on to node F. In step 6 at node F, again the value of alpha will be compared with left child, which is 0, and max of 3 comma 0 is equal to 3, and then compare with right child, which is 1, and max of 3 comma 1 is equal to 3. Still alpha remains 3, but the node value of F will become 1. Here's the picture shows the step 4, 5 and 6. In step 7, node F returns the node value 1 to node C. At C, alpha is equal to 3 and beta is equal to plus infinity. Here the value of beta will be changed. It will compare with 1. So min of infinity comma 1 is equal to 1. Now at C, alpha is equal to 3 and beta is equal to 1, which satisfies the condition alpha greater than or equal to beta. So the next child of C, which is G, will be proved, and the algorithm will not compute the entire subtree G. Here the picture of the above step. Final step, C now returns the value of 1 to A. Here the best value for A is max of 3 comma 1 is equal to 3. Following is the final game tree, which is showing the nodes which are computed and nodes which has never computed. Hence the optimal value for the maximizer is 3 for this example. The effectiveness of alpha beta pruning is highly dependent on the order in which each node is examined. Move order is an important aspect of alpha beta pruning. It can be of two types: worst ordering and ideal ordering. Worst ordering. In some cases, alpha beta pruning algorithm does not prune any of the leaves of the tree and works exactly as min-max algorithm. In this case, it also consumes more time because of alpha beta factors, such as move of pruning is called worst ordering. In this case, the best move occurs on the right side of the tree. The time complexity for such an order is O of Bm. Ideal ordering. The ideal ordering for alpha beta pruning occurs when lots of pruning happens in the tree and best moves occur at the left side of the tree. We apply DFS, hence it first search left of the tree and go deep twice as min-max algorithm in the same amount of time. Complexity in ideal ordering is O of Bm by 2. Rules to find good ordering. Occur the best move from the shallowest node. Order the nodes in the tree such that the best nodes are checked first. Use domain knowledge while finding the best move. Example, for chess, try order, captures first, then threats, then forward moves, backward moves. We can bookkeep the states as there is a possibility that states may repeat. These are the rules to find good ordering. Thank you.